In this video, we are going to examine structure of some reactive intermediates that are derived from hydrogen and carbon, and we will also look at structure of simple inorganic molecules. Those would be ammonia, water, and hydrogen halides. Reaction intermediates are short-lived, unstable species that are formed in the course of a chemical reaction. They are formed from stable species. They have very short lifetime, typically much less than a second, very short fraction of a second. Sometimes if they last a second or a few seconds, that's long time for an intermediate to last. Those would be more stable intermediates, but still they are unstable. And sometimes reaction pathway involves sequence of short-lived, unstable intermediates before stable products are formed. Now we are going to briefly examine reaction intermediates derived from hydrogen and carbon, because those are the most important for study of organic chemistry. Reaction intermediates derived from hydrogen are hydrogen ion, hydride ion, and hydrogen radical. So hydrogen ion is a result of loss of an electron from hydrogen atom. So hydrogen ion is positively charged species, and actually it's identical to proton. So sometimes we call it hydrogen ion and sometimes proton. Both terms are fine and both terms are in use. In organic chemistry, actually we more frequently use the term proton. Hydride ion is negatively charged ion and is a result of hydrogen atom gaining an electron. When hydrogen atom gains an electron, then resulting hydride ion has hydrogen with its duet field, and of course, as already said, a negative charge. Finally, hydrogen radical is identical to hydrogen atom. Keep in mind that under ordinary conditions, hydrogen is in form of H2 molecules. So H2 molecule has to be broken up into individual atoms to obtain hydrogen radical. Species like these that have unpaired electrons, and that's the definition of a radical, species with unpaired electron. So species like these that have unpaired electrons and that are identical to atoms could be either called radicals or atoms. Besides hydrogen, commonly encountered atoms that are both atoms and radicals are halogens: fluorine, chlorine, bromine, or iodine. Usually we call them atoms, unless we want to emphasize that they are radicals. Now, reaction intermediates obtained from carbon are a little bit more complex in structure. They involve carbocation, carbanion, carbon radical, and various carbenes. We will examine them on simplest example on compound, or not compounds, but intermediates derived from methane. So you already encountered methane earlier in this chapter. You know its formula, including Lewis structure. So carbon is bonded to 4 hydrogens with single bonds. If one of the bonds is broken heterolytically, that means one of the atoms leaves with both electrons, leaving the other atom deficient, then the resulting species are either methyl cation or anion. If we formally break bond, carbon-hydrogen bond, in such a way that hydrogen leaves with the electron pair, then carbon is left electron deficient, and that's methyl cation. So methyl cation has a positive charge. Methyl anion is a result of heterolytic bond breaking, where hydrogen leaves as a proton and leaves electron pair on the carbon. So that will be methyl anion. Result of homolytic bond breaking results in formation of either methyl radical or, less commonly, methyl carbene. Methyl radical is result of breaking of one bond homolytically, which means evenly, so each atom is left with one electron from that bond. So methyl radical has carbon with an unpaired electron. Methyl carbene is result of breaking of 2 such bonds, and so such carbon atom has 2 electrons. Those 2 electrons may or may not be paired up, as you will see in a minute. So methyl radical and methyl carbene have no charges. Now we're going to examine carbon intermediates in a little bit more detail. So first we will look at methyl radical. So methyl radical has 3 substituents. It is sp2 hybridized and has trigonal planar geometry, which means 3 bonds on carbon, those are carbon, in this case carbon-hydrogen bonds, have trigonal planar geometry. Methyl radical also has an empty orbital, and that orbital is unhybridized atomic p orbital. Now, interesting fact is that some chemists chemists will argue that there is no such thing as an empty orbital. The reason behind that argument is that an orbital is defined as a region of space where probability of finding an electron is 90%. So, strictly speaking, it means that if there is no electron, there can be no orbital, because if there is no electron, there is nothing to be found in that region of space. You should understand empty orbital as a region of space that will accept a free electron pair. These are unstable species, short-lived species, so carbocations like methyl cation don't last very long. They very quickly react to accept an electron pair. So electron pair will be donated to empty p orbital. And that's how you should understand any empty orbital in general. That's region of space that in the course of reaction will accept an electron pair. Next species that we are going to look at is methyl radical. Now, there is a little bit of disagreement about structure of methyl radical. You should accept this simpler view. We are not going to cover more complex view. And according to simpler view, methyl radical is sp2 hybridized, which means that just like methyl cation or any other carbocation, it has trigonal planar geometry. So 3 bonds on carbon have trigonal planar geometry. And free electron is in unhybridized p orbital. So it's very important that you know electronic configuration and geometry of the molecule and of course hybridization. Finally, methyl anion is a little bit different from the previous two species in that it is sp3 hybridized. And being sp3 hybridized, it has trigonal pyramidal geometry. Note that free electron pair does not count when we look at geometry of a species, in this case ion. We are only looking at positions of atoms. And looking at positions of atoms, this is trigonal pyramidal geometry. So note that free electron pair needs an entire hybrid orbital to itself. So empty orbital or single electron were in unhybridized atomic p orbital. But free electron pair needs entire hybridized orbital to itself. That's because of the repulsion between electrons. And so free electron pair is in hybrid sp3 orbital. So very important sp3 hybridization. Can't emphasize that enough. Finally, we have carbene species. They are much less common and they are not encountered much in this course. So carbene is carbon that forms 2 bonds to hydrogens and have 2 electrons. So it is not a charged species. Carbene could exist in 2 forms. As a singlet carbene, in singlet form 2 electrons are paired up. So as you have just seen in a minute, electrons that are paired up, electron pair, requires hybrid orbital to itself. Which means that singlet carbene is sp2 hybridized, geometry is bent. Because we are looking only at hydrogen, carbon, hydrogen geometry, and that's bent geometry. So sp2 hybridized, free electron pair is in hybrid sp2 orbital, and empty orbital is atomic p orbital. Finally, triplet carbene has also bent geometry, but now each of the free electron pairs is in hybrid sp3 orbital. So hybridization is sp3, and each of the free electrons is in hybrid sp3 orbital. That's simply because we can't have 2 different orbitals if it were sp2 hybridized, 2 different orbitals, and each of them having 1 electron. 2 orbitals have to be identical. Hybridization, keep in mind, is mathematical operation. So 2 identical orbitals, they have to be sp3. Next, we are going to examine bonding in ammonia. In a molecule of ammonia, nitrogen atom forms bonds to 3 hydrogen atoms. So formula of ammonia is NH3, and all 3 bonds are of equal length and equal strength. So that's explained by hybridization of nitrogen's atomic orbitals. Unlike carbon atom, there is no promotion of an electron from 2s to 2p orbital. Nitrogen has free electron pair when we consider nitrogen's valence electrons. Nitrogen has a free electron pair in the 2s orbital and 3 unpaired electrons in 3 2p orbitals. If an electron were promoted from 2s to 2p orbital, it would simply pair up with one of the p electrons. It means that process would use up energy, but number of unpaired electrons would remain the same. And so there is nothing to be gained because additional bond cannot be formed, and there is no compensation for energy that is used up to promote electron if additional bond is not formed. For that reason, there is no promotion of electron. Simply, we only carry out mathematical operation of hybridization, and 4 identical orbitals are formed, 4 sp3 orbitals. One of those sp3 orbitals is filled and contains electron pair. Remaining 3 contain unpaired electrons and can be used for bonding. Geometry of electron cloud, that means 3 bonds and free electron pair, is tetrahedral. So here you can see NH3, molecular formula of ammonia, then Lewis structure, nitrogen with 3 bonds to hydrogen and free electron pair, and finally geometry of the electron cloud. It's tetrahedral, so 3 bonds and free electron pair have tetrahedral geometry. But geometry of the molecule itself is trigonal pyramidal, and that's again because free electron pair does not count, the same way as in case of methyl anion. Only atomic nuclei are considered when considering geometry of the molecule. So bond angles, hydrogen, nitrogen, hydrogen, bond angles are 107.3 degrees. So you will notice that bond angle is slightly smaller compared to ideal tetrahedral angle of 109.5 degrees. This is explained by electron repulsion between electron pairs. Free electron pair requires more space compared to electrons in bonds, because an electron pair in a bond has at the other end atomic nucleus, positively charged atomic nucleus, in case of hydrogen proton, that attracts those electrons. And so those electrons are attracted closer to the nucleus and occupy less space. On the other hand, in case of free electron pair, we have 2 electrons that occupy same regional space, an orbital, and they repel each other electrostatically. So they require a little bit more space. So they expand to take up more space to minimize electrostatic repulsion. But by doing that, they force 3 remaining bonds closer together. And that's the reason why hydrogen, nitrogen, hydrogen bond angle closes a little bit and is a little bit smaller compared to ideal tetrahedral bond angle. Here is model, ball and stick model of molecule of ammonia, and so you can see that electron pair, free electron pair of nitrogen does not play a role in geometry of the molecule, and you can see clearly that the geometry of the molecule is trigonal pyramidal. And here is a space filling model. So you can see that the molecule of ammonia is roughly spherical. Now, there is another species, and that's ammonium ion, that is obtained by protonation of molecule of ammonia. So a free electron pair on nitrogen can form a bond to proton, and so ammonium cation is result. Ammonium cation is tetrahedral, and it's an ideal tetrahedron because 4 nitrogen-hydrogen bonds are identical. So bond angle is ideal tetrahedral angle of 109.5, and all 4 bonds have identical lengths and strengths. Nitrogen is again sp3 hybridized. Here is molecular model, ball and stick model of ammonium ion, and you can see 4 bonds of identical length, and you can see bond angles, ideal tetrahedral angles, and also space filling model. Note that ammonium cation looks just like methane. Its geometry and electronic configuration is identical to that of methane. Molecules like these that have electronic configurations that are identical are called isoelectronic. So ammonium ion is isoelectronic with methane, and ammonia is actually isoelectronic with methyl anion. In a molecule of water, oxygen atom forms bond to 2 hydrogen atoms. Both bonds are of equal lengths and equal strengths. So this is explained by hybridization of oxygen atomic orbitals. So oxygen in ground state has electronic configuration of 1s2, 2s2, 2p4. So 2s2, 2p4 are valence electrons of oxygen, and here we have energy diagram of 2s and 2p electrons of oxygen, you can see that in ground state 2s electrons are paired up, and one of the 2p orbitals contains electron pair. Remaining two 2p orbitals have unpaired electrons. We explain bonding in water, in general in oxygen compounds with single bonds, as a result of sp3 hybridization. So again, 2s and 2p orbitals hybridize to form 4 equal energy sp3 hybrid orbitals. Now two of those 4 hybrid orbitals have electron pairs, free electron pairs, and those free electron pairs cannot participate in bonding. Remaining 2 have unpaired electrons, and those 2 are the ones that form bonds. Just in case of nitrogen, there is no promotion of electron because that would require energy, and there would be nothing in return because number of unpaired electrons would remain the same. So if electron is promoted from 2s to 2p, then it would pair up with one of the 2p electrons, and we would still have only 2 unpaired electrons. So molecular formula of water is H2O. In the middle you have Lewis structure, oxygen with 2 single bonds to hydrogens and 2 free electron pairs. Note that the shape of the electron cloud is tetrahedral, so 2 free electron pairs and 2 oxygen-hydrogen bonds have roughly tetrahedral shape. But the shape of the molecule is bent because, again, free electron pairs are not considered when considering geometry of a molecule. And hydrogen-oxygen-hydrogen bond angle is 104.5, so even smaller than bond angle in ammonia. And again, that's explained by electrostatic repulsion from the free electron pairs. Now we have 2 free electron pairs that require more space because of the electrostatic repulsion. And as they expand to occupy more space to minimize repulsion between their individual electrons, that forces oxygen-hydrogen bonds closer together. And that's why hydrogen-oxygen-hydrogen angle closes a bit and ends up being 104.5 degrees. Here is the molecule, ball and stick model of the molecule, and you can clearly see that the geometry is bent and 2 bonds are identical. And here is space filling model of oxygen molecule. Now, when it comes to hybridization of atoms with multiple bonds, you may be wondering, how do we know that hybridization of oxygen and nitrogen in previous compounds was sp3? Why we won't assume that it's sp2 or sp? So there is a simple formula that will help us determine hybridization of carbon, nitrogen, or oxygen atoms. So this formula applies in general to carbon, nitrogen, and oxygen atoms. It may apply to other atoms, but it's not general, so don't apply it always. So it's sp. So hybridization is sp, and then 3 minus number of pi and p orbitals. So you look how many orbitals are on a particular atom, and you add up total of pi and p orbitals on that atom. You subtract that from 3, and that's the hybridization. So here are some examples. So these are all examples of sp3 hybridized carbon, nitrogen, and oxygen atoms. You will notice that these atoms have 0 p and pi orbitals. There are no p and pi orbitals on these atoms. Then some examples of sp2 hybridized carbon, oxygen, and nitrogen atoms, and each of those atoms has either 1 p orbital. So first 2 carbon atoms have atomic p orbital, unhybridized p orbital, and that's why they are sp2 hybridized. Middle carbon, third carbon in this order, has molecular pi orbital, so that's why it's sp2 hybridized. And oxygen and nitrogen each have molecular pi orbital, so they are sp2 hybridized. And finally, examples of sp hybridized atoms. Those are atoms that have 2 p or pi orbitals, in general 2 pi orbitals. So each of those examples of carbon and nitrogen atoms have 2 pi orbitals on that atom, and as a result they are sp hybridized. So far we have examined geometry of some of the compounds of carbon, nitrogen, and oxygen. One way to predict geometry of a molecule is from the hybridization of the central atom. Another is by application of Vesper method. So far we were looking at hybridization of the central atom, and that's how we were predicting geometry. And that's what we'll be usually doing in this course. Still, Vesper method is quite useful, and it is covered in general chemistry course. So hopefully you are familiar with this, and this will hopefully remind you of that method. You may want to review it, so you may want to look up your general chemistry textbook and remind yourself of this method. So geometries of small molecules with up to 5 substituents on the central atom are shown in this table. So we are looking at number of valence shell electron pairs, then what is the hybridization that corresponds to it, which is how we are determining geometry, and then from the number of substituents we can determine geometry of the molecule. So with 3 substituents you can see that geometry is either bent or trigonal planar, depending on the number of bonds and free electron pairs. With 4 substituents, geometry could be bent, trigonal planar, or tetrahedral, again, depending on the number of bonds and free electron pairs. And finally, 5 substituents, geometry could be linear, T-shape, seesaw shape, or trigonal bipyramidal. Finally, we are going to examine properties of hydrogen halides. There is only a single hydrogen-halogen bond, so there is no geometry to be considered. In this case, we are concerned with trend in bond lengths and bond strengths. Smallest hydrogen halide is hydrogen fluoride. It has shortest and strongest bond. In general, length and strength of the bond are inversely related. So short bond is strong bond and long bond is weak bond. And the next in strength is hydrogen chlorine bond. It is longer and considerably weaker compared to carbon fluorine bond. So the observed trend in length and strength of hydrogen-halogen bonds is explained by properties of atomic orbitals that overlap to form molecular bonds. So length and strength of hydrogen-halogen bond or any other bond depends on the efficiency of the overlap of the corresponding atomic orbitals that form that bond. Efficiency of the overlap in turn depends on 2 factors. One is relative sizes of the 2 orbitals that are overlapping. So if they are similar in size, they will have better overlap as opposed to orbitals that are very different in size, one large and one small. And the other is the phase of the orbital. Are the orbitals that are overlapping in the same phase? So in case of carbon-fluorine bond, we can see that 2p orbital of fluorine, which is a valence orbital of fluorine, overlaps very well with 1s orbital of hydrogen. They are very similar in size, and of course hydrogen 1s orbital has only one phase, and fluorine lobe that overlaps with that orbital, with 1s orbital of hydrogen, also has only one phase. So there is very good overlap. Orbital is small in size, 2p orbital of fluorine is small in size, so result is strong and short bond. Now next, when we consider chlorine, we can see that 3p orbital of chlorine is much larger and appears rather differently. Each what you would consider lobe on each side actually is split into 2 slices, 2 lobes that have opposite phases. So first there is size mismatch. 3p orbital of chlorine is much larger compared to 1s orbital of hydrogen, so orbital overlap is less efficient. And in turn also the part of the orbital that points towards 1s orbital of hydrogen that can overlap with it has 2 phases. One is in phase with hydrogen and can form constructive overlap, form a bond with hydrogen, but the other one is out of the phase and cannot constructively overlap with hydrogen's orbital to form a bond. So the result is much longer and much weaker bond. And then that trend continues going to bromine, which utilizes 4p orbital, and iodine, which utilizes 5p orbital. So as we go down the group of the halides, halogens, bonds to hydrogen becomes progressively longer and weaker. So hydrogen-fluorine bond is very short, 0.918 angstroms, and very strong. 135 kilocalories per mole. That's a very strong bond. Hydrogen chlorine, much longer, 1.274 angstroms, and much weaker, 102 kilocalories per mole, although this is still a strong bond. Hydrogen bromine is actually rather long, 1.408 angstroms, and rather weak, 87. That bond can be easily broken. Finally, hydrogen iodide bond is extremely weak and long. Its length is 1.608 angstroms, and its strength is only 70 kilocalories per mole. Even visible light may be able to or can break this bond, so hydroiodic acid has to be kept in dark bottles in a fridge to prevent it from decomposing. This completes our review of bonding, and in the next chapter we'll be looking at chemical formulas.